What's up, goons and goonesses? Today we are going to talk about finding the zeros of polynomials. I'm going to warn you right now that this is probably the hardest lesson we've done so far. So you're going to want to close all your lo-fi hip-hop tabs, close all those funny videos you're watching, put your phone down, turn off TikTok, hang up with your grandma, pay attention, because we're going to put some hair on your butt today, and there's no two ways around it. Okay? Finding zeros is a labor-intensive task. It doesn't mean it's going to be crazy hard, but there's a lot of steps and a lot of stuff you have to get right. So it's important that we are alert, focused, paying attention, right? Your face should look like this. You should be all mad, right? Like, I'm focused. I'm focused. Okay. So we are going to learn this stuff today, and it's going to be rad. Hang on, I got to put hair on this guy. Rad. He's got one earring, right? That's how you know he's a thug. All right, anyway, cool. So we're going to learn zeros of polynomials. I'm going to tell you the steps, and I'm going to refer back to these steps repeatedly. See how it says try, though? That means you might have to think a little outside the box on your own on some of these questions. They can get a little bit tricky, but I'm going to give you strategies to try and help subvert the trickiness of the problem. All right, we're going to attack these head on, but sometimes it's hard. You know, life's hard. You better find that out now rather than later. Okay, so step 0 is find one of the roots. This is step 0 because on your homework, the homework already tells you one of the roots. So you don't really need to do this step for yourself, with the exception of, I think, one homework question. So that's why it's here. I'm going to go over a couple ways to find this root, but we're not going to do it the hard way. The hard way is using the rational roots theorem. This thing is very labor intensive. It's where you find your p's and your q's, and you put p's over q's, and it's all the factors of p and all the factors of q. I'm going to try and avoid this because it's very labor intensive, and we can do it an easier way because we live in 2020 and technology exists. But if you're going to be a math major someday, like you want to be a PhD mathematician and do math for the rest of your life, I'm totally doing you a disservice by not showing you how to do this. So when you're in grad school and it comes up, what is the rational roots theorem and how do you use it? Come back. You know where I'm a teacher at. I'll fix it then. Okay. Actual step 1 is we're going to have to take out the root that they're going to tell us, and we're going to do that by dividing it out. So you have to know how to do polynomial division, but we're going to review that on the next slide. So don't trip about this. I'll teach you how to do it again. But realize you're going to have to do some dividing. After we do the dividing, we're going to hope that it factors. If it doesn't factor, don't worry. We've got some backup strategies on how to figure out another root. It's kind of like go back to step 0 and start again. But if it factors, woohoo, great, that's awesome. We're happy campers, right? We got like those, oh my God, so happy face. Okay. Step 3 is once we get this polynomial reduced to a quadratic, that means the biggest term is x squared, then we're either going to factor that thing to death or we're going to just bludgeon it to death with the quadratic formula. Either way, we're going to get the answers we want. Okay. So here are our steps. Here's what we're going to try and do, but keep in mind math is hard and sometimes we got to use our brains. So let's start by talking about what is the fundamental theorem of algebra. So this is not the fundamental theorem of algebra you'll find on Wikipedia, because the one on Wikipedia is too hard for us. It says things like, this is equivalent to complex numbers having closure under all arithmetic or something like that. And there's like 18 other vocab words in there that we're not going to explain. So what you need to know is that the fundamental theorem of algebra says that the number of roots, so the things we're looking for, of a polynomial is equal to the degree of that polynomial. And degree is just the biggest exponent. Right? So if we saw something like f of x equals 4x to the 5th minus 7x to the 4th plus 18x minus 2. Because the biggest exponent here is a 5, that means we're going to have x equals 5. All right, you get the idea. 5 of those. There are going to be 5 roots. They could be repeated. It could be like x equals 2 and then x equals 2 again. It's called having a multiplicity of 2. But in general, you just want to take a peek at this thing and figure out how many answers am I expecting to get, and do I have all of them? All right, and that's as much as we need to say about the fundamental theorem of algebra. All right, so just like I promised, we're going to go over how to do some division before we get into actually solving anything, because we're going to have to do this process a couple of times to make our problems work out the way we want them to. Okay, so we are given that x equals 3 is a root of this polynomial, and what we're doing right now is step 1. We are removing the known root by dividing it out. Okay. So the way we do this is you take your known root, and that number, whatever x is equal to, goes outside this L thingy, so we put the 3 right there. Then across the top of this L, we're going to put the coefficients of our polynomial. So the coefficient of x cubed, there's nothing there, so it's an invisible 1. So we're going to put our 1, negative 6, negative 1, and positive 30. Okay. Now we're going to do the synthetic division. And the way you do synthetic division is any numbers that get underneath the L, you multiply them by this 3 outside and put them under the next number. And you're going to say, well, Mr. Barton, there's not a number here. This first one, don't do anything to it. Just drop it straight down. Now that's under the L, it gets multiplied to the outside number. So 3 times 1 is 3. And then here we are adding, or you're doing whatever the signs say. So this would be negative 6 plus 3. So that would be negative 3. Now it's under the L again. So we multiply to the outside number. 3 times negative 3 is negative 9. Then negative 1 plus negative 9, this is just negative 10. And we multiply again. 3 times negative 10 is negative 30. And then 30 minus 30 is 0. All right, so we've done most of the synthetic division. Now we have to turn this back into a polynomial. The way you do that is whatever power you had there, reduce it by 1, and then you just throw your x's in descending exponent order onto these numbers. This last one is always a remainder. And hopefully that's not important today, because your remainder should be 0. Because if this is a root, that means that a factor is being taken out. It should go in evenly with a remainder of 0. If you don't get a 0 here, you messed up. Okay, so look here, our exponent's 3. Decrease that by 1. So we're going to start with x squared. So we have 1 x squared. Then we go down another power. So this is minus 3 x to the first. So down another power, minus 10, no x's, x to the power of 0. And then you're done with synthetic division. Cool? Remember that? Not too bad? All right. So that's just the synthetic division. We're going to leave that one there just for, there you go, it's chunked. Okay, so we've practiced step 1. Now, step 2 would be factor if possible, and hopefully you guys aren't scared of trying to factor this thing, right? So we'd factor if possible, and then we'll find the rest of the roots from there. Okay, now that we're done with this easy problem, let's go take a look at the full thing all together, finding all the roots of a problem. In this problem, it says, given that x equals negative 3 is a root, sorry, there should be is a root, find the remaining roots of this thing. So the first thing we notice, since our largest exponent is a 4, that means there are 4 roots total, and they already told us 1. So we are looking for 3 more. So we should have 3 different answers here for what the other x's are. Maybe not different. It could be like 2 and then 2 again, but we're looking for 3 answers. All right. So step 0 is done for us. They told us a root. Now we need to take the root out of this polynomial and then try and find the rest of them. So the first step is take this root out of this by doing the synthetic division we just went over. So we put the -3, that's the root, on the outside. We put our coefficients across the top. So 3, 16, 9, -36. Drop the first number down. Multiply to the outside. And then we're going to add, so this is 7 times -3 is -21. And 9 minus 21 is 12, -12. Times -3 is +36, and we get 0. Again, this 0 should always happen on that last one. If these don't cancel, you mess something up over here, and you need to go back and check your multiplication and adding. All right, now we need to turn this thing back into a root, or rather a polynomial, excuse me. So we started with 4, so we're going to go ahead and just decrease our exponents by 1. So this could be 3x to the third plus 16, whoops, sorry, I'm looking up here, not down here. Back up a little bit. Sorry, 3x cubed plus 7x squared minus 12x, right? And then plus 0, x to the first plus 0. Technically, I should put a 0 here because there's plus 0 x to the whatevers, but 0 times anything is 0, and it's 0 again, so it'll still work out. Okay. Now, this is the polynomial that we have to find the remaining 3 roots of. Okay. So we have finished step 1. We've removed the known root. Now it says factor if possible. So if we go look at this, we want to see, can we factor this? And you're looking, oh, how do I factor 3 and 7 and 12? That's kind of tough, Mr. Barton. But one thing we can notice here is that every single one of these terms has an x in it, so they have a GCF. The GCF is x. So we're going to take that x out. So this will become y equals, pulling the x out of the parentheses just decreases all of these x's by 1 power. We're removing 1 x from each. So 3x squared plus 7x minus 12. Wonderful. Now we have to find the rest of the roots from here. So we have 2 options. We can try and factor that using complex factoring, or if you can't factor, we are going to use the quadratic formula because this is a quadratic now. Right? And we can tell it's a quadratic because of the x squared. So if we try and factor this, let me think for half a second. Is this going to work? Are we going to be able to factor? Let's pause and check before I lead you guys astray. So I bet you didn't even notice the pause. It actually doesn't factor. I checked. We would try and do complex factoring where you multiply the 3 to the end and you get 36 here, and then you try and factor that thing. But unfortunately, the 36 isn't going to do anything with the 7. So what we need to do to find the zeros of this thing is, unfortunately, we have to beat it to death with our quadratic formula. So we need to find a, b, and c, plug them into our quadratic formula, and that will give us our zeros. Okay. So a is 3, b is 7, and c is -12. We're going to plug this into our quadratic formula. So we have negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. This is going to give us our roots. We're going to get 2 of them because of this plus and minus right here. One will be the plus version, and the other one will be the minus version. So we just need to simplify this thing, and it'll give us the rest of our roots. So we have x equals, keep our -7, plus or minus. Let's simplify this. 4 times 3 is 12, So this is negative 12 times negative 12. That's positive 144. So we have 144 plus 49. So that's 3, carry the 1, 9, 1. So plus or minus square root of 193 over 6. Okay. So these are two of our roots. And just in case it's not 100% clear, the two roots are negative 7 plus radical 193 over 6 and negative 7 minus radical 193 over 6. These are two of our roots. And you're going to say, but Mr. Barton, you said there were 3 roots because you underlined that 3 right there. Where's the third root? I only see 2 of them. So let's go back. This x right here is a factor. So to get the root from this thing, we set it equal to 0. So x equals 0 is our third root. So our 3 roots are x equals 0, x equals negative 7 plus radical 193 over 6, and negative 7 minus radical 193 over 6. So anytime you have a GCF of x, you're going to get x equals 0. That could be an easy one for you to look for right away. Since there's an x there, an x there, an x there, and an x there, you know x equals 0 is one of the answers, and you can just start by writing that down. Unfortunately, these two roots are going to be pretty ugly most of the time, so it's going to be a little challenging for you to find these. But just stay calm, try and find your a, b, and c and use quadratic formula. Sometimes this will even factor nicely for you. All right, now let's look at a harder example. So let's talk about that tip I just told you. If there's a GCF of x in your problem, x equals 0 is one of the roots. So, well, okay, there's all our x's. The problem here, the reason why this is a harder example is because that's the one they tell us. So let's factor out our x, and then we'll see how do we get the rest of them. So if I factor or take the GCF of x out of this, we're going to have y equals x, and we just decrease all these exponents by 1. So x to the third plus 11x squared plus 26x minus 20. All right, so because we have this GCF of x here, x equals 0 is one of our roots. We are responsible for finding the other 3 of them, and this is a hard problem because we're not going to be able to factor this. If you try your factoring by grouping, the GCF here is x squared, and the GCF here is 2. So you're not going to get matching stuff. It's not really going to work out. So your typical factor by grouping isn't going to work here. And I don't know how to factor this otherwise. So what we have to do is we have to figure out another root to take out of this thing. The way you can do that is P's and Q's. P is, let me think about this, P's, yeah. P are all the factors of your last term, and Q are all the factors of your first term. We're not going to do that because it gets really, really tedious. So here's how you are going to do it. We need to find a root of this thing. Luckily, you live in 2020, and you can just graph this thing and look on a graph. Where does it cross the x-axis? So we want to know, where does this thing go across our x-axis? So we type this thing into Desmos or a graphing calculator or anything that'll graph for us, and we look at it. Luckily, I've already done that. Here's our beautiful graph. So we can see it crosses right there, and right there. This one and this one are really ugly decimals. I think it's like negative 0.606 and 0.606 or something like that. Negative 6.06, something like that. So these ones you're not going to be able to read off a graph. They're decimals. I want the exact value, which means they have to have radicals in them. They have to be ugly and gross like this one on the last page. So we can't use these ones. We can't read them accurately enough. So we are left with that one, which is exactly halfway between -6 and -4. So it's saying our last root is x equals -5. So this is one of our three answers we're looking for. And the way we figure that out is by graphing this and then finding the nice one where it crosses the x-axis. So now we basically have been told another root. We're going to take it out of this and then try and factor what's left. So let's take out our root of -5. -5 goes outside our synthetic division. We write our coefficients across the top. And now we do the synthetic division. So bring down your 1, multiply to the -5. Do your subtraction, multiply to the -5. Do your subtraction, multiply to the -5. Make sure these cancel, otherwise you did something wrong. All right. So we were at x cubed. We took a linear term out, so it goes down by 1. So we have 1x squared plus 6x minus 4 with a remainder of 0. Now that we have this thing, we have to find the last two roots, which are this root and this root. And this isn't going to factor. If we look at our factors of -4, our factors are 1 and 4, 2 and 2. We can't make a 6 out of these numbers. So we have to hit this thing with the quadratic formula. So a equals 1, b equals 6, and c equals -4. We're going to plug these into our quadratic formula. X equals -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Now we're going to simplify this, and this is going to give us our last two roots. So we have, -6 plus or minus the square root of -4 times 1 times -4 is positive 16 when you simplify. So this is going to be 36 plus 16. It's 52 over 2. All right, and then we want to check this thing to see if it simplifies. 52 is 2 and 26, 2 and 13. Because it's a square root, we're looking for pairs of 2. So we could take a 2 out of this and leave the 13 in the radical. So this is going to be -6 plus or minus 2 radical 13 over 2. And then we can reduce this because the denominator goes into both of these coefficients. So we divide both coefficients by 2, and we get -3 plus or minus radical 13. And this is, there are two of them, our last two roots. So our roots are these two roots and this -5. All right. I understand that's a lot to digest. Finding roots can be a little tricky because there are so many steps and there are a lot of different things you have to be careful of, different ways you have to approach finding some of the roots. So I'm pretty sure you guys are going to need some help. Make sure you hop back in that WebEx, ask me some questions, even open your homework and say, Mr. Barton, you know, as wonderful as that video was, really, I was blown away, Mr. Barton. I was so impressed. But unfortunately, I just couldn't quite wrap my head around it. Do you think maybe we could have a dialogue where we discuss the intricacies of finding roots of polynomials? And I would love nothing more than to sit and talk about that with you. So please go ask me some questions.